Hello, everyone, and welcome. Today, we are diving deep into one of the most fundamental topics in all of chemistry: acids, bases, and salts. You find these substances absolutely everywhere, from the science lab to your own kitchen, so let's get right into it and break down exactly how they work. Okay, so let's get focused. Everything we're talking about today comes straight from Chapter 2 of the NCERT Class 10 Science textbook. And I really want to stress this. This is not just another school lesson. The concepts we're covering are absolutely critical, whether you're gearing up for your board exams, tackling competitive exams like the UPSC, or you just want to build a seriously solid foundation in science.
So here's our game plan. We're going to start with the basics. What even are acids and bases? Then we'll jump into the most important chemical reactions you need to know. After that, we'll uncover the surprisingly crucial role of water, decode the pH scale, and we'll wrap up with a quick look at all the amazing chemicals we get from something as simple as common salt. Let's do this!
First things first, what are we actually talking about when we say acids and bases? Before we get into all the cool reactions, we have to start with the fundamentals. How do we even tell these things apart?
You've probably already got a sense for this from your daily life. Just think about the sour kick of a lemon. That's citric acid. Yep, acids are sour, and their classic lab test is turning blue litmus paper red. Bases, on the other hand, are bitter, and they often feel kind of soapy or slippery to the touch, like if you mix baking soda with water. In their test, they do the opposite. They turn red litmus paper blue. And that litmus paper, by the way, comes from lichen, so it's our go-to natural indicator. Now this slide right here, this is pure exam gold. Seriously, you're going to want to memorize this. It's your cheat sheet for the synthetic indicators we use in the lab. So besides litmus, we have phenolphthalein and methyl orange. Check it out. Phenolphthalein is totally colorless in an acid, but put it in a base and boom, it turns this bright, vibrant pink. Methyl orange is red in an acid and it turns yellow in a base. You have got to know these color changes cold.
All right, so now we can identify them. Let's see what they can do. We're moving into Section 2, where we're going to get into the key chemical reactions. This is really the heart of the chapter, with the equations that you'll see pop up time and time again in your exams.
So, let's picture a classic lab experiment. Imagine you've got a test tube with some dilute sulfuric acid, and you drop a few zinc granules in there. What do you think happens? What's going on when an acid meets a metal? Here is the key formula you have to remember. The acid reacts with the metal, and it produces two things: a salt, in our example that would be zinc sulfate, and hydrogen gas. So how do we know for sure it's hydrogen? Well, there's a classic test. If you bring a burning candle to the mouth of the test tube and you hear a sharp pop sound, that's your proof. That's the hydrogen gas. Okay, that's great for pure metals, but what if the acid reacts with something like limestone or even chalk? You know, a metal carbonate. The reaction is pretty similar, but with one major difference. You still get a salt and water, but this time the gas that's bubbling off is carbon dioxide, and the surefire test for CO2 is to bubble it through lime water. If it turns milky, you've got carbon dioxide. And all this leads us to the most fundamental reaction of them all: neutralization. It's exactly what it sounds like. When you mix an acid and a base, they literally neutralize each other's effects. A base plus an acid gives you a simple, neutral salt and water. It's the exact same reaction that happens when you take an antacid to soothe an upset stomach. So let's move on to Section 3, the role of water. Here's a little riddle for you. Why is it that dry hydrogen chloride gas doesn't act like an acid at all, but the second you dissolve it in water, it becomes hydrochloric acid? Let's find out why H2O is the secret ingredient.
The secret is all about ions. You see, an acid or a base can only show its true properties when it can break apart or dissociate into these little charged particles called ions, and water is the key that unlocks this whole process. In water, acids release their hydrogen ions and bases release their hydroxide ions. It's these free-floating ions that give them all their characteristic properties, including the ability to conduct electricity. So the bottom line is simple. If you don't have water, you don't get ions, and you don't get any acidic or basic behavior.
And speaking of acids and water, listen up, because this is a safety rule you absolutely cannot forget. When you mix a concentrated acid with water, it's a super exothermic process. That's just a fancy way of saying it releases a ton of heat really, really fast. Now, if you do it the wrong way and add water to the acid, the heat can instantly boil the water, causing the whole mixture to splash violently out of the container. This can cause serious burns, so the rule, always, is to add acid to water, A to W. Never, ever the other way around.
So we know what they are, we know how they react, but how strong is a particular acid or base? For that, we need some way to measure it. And that brings us to Section 4, the pH scale.
The pH scale is a really straightforward scale from 0 to 14. That little p in pH actually stands for potens, which is the German word for power, referring to the power of hydrogen ion concentration. Right in the middle, a pH of 7 is perfectly neutral. Think of pure water. Anything below 7 is acidic, and the lower the number, the stronger the acid. And anything above 7 is basic or alkaline, with the higher numbers meaning a stronger base.
So why should you care about this? Because pH is literally all around us and inside us. Our stomachs use incredibly strong acid with a pH around 2 to digest food. Tooth decay actually starts when acid produced by bacteria drops the pH in your mouth below 5.5. We hear about acid rain. That's just rainwater with a pH lower than 5.6, and it can be devastating for rivers and lakes. Even the soil in a garden needs to be at the right pH for plants to grow properly. It's this delicate chemical balance that affects everything. All right, let's bring it home with our final section. We're going to see how one incredibly simple substance, just plain old table salt, sodium chloride, is the starting point for a whole range of really important chemicals that we use every single day. First up, we have bleaching powder. It's made by passing chlorine gas over dry slaked lime, and its uses are pretty much right there in the name. It's a fantastic bleaching agent for things like cotton textiles and paper pulp, but maybe its most important job is disinfecting our drinking water, keeping it safe for all of us.
Next is one you definitely have in your kitchen. Baking soda. Its chemical name is sodium hydrogen carbonate, and it is so versatile. When it's in baking powder, it reacts to release carbon dioxide gas, which is what makes your cakes and bread light and fluffy. And because it's a mild base, it's a key ingredient in antacids to neutralize stomach acid. That same CO2 releasing ability also makes it useful in some types of fire extinguishers.
Then we have washing soda. Now, if you look closely at its chemical formula, you'll see those 10 H2O molecules at the end. That's called water of crystallization. It just means water is actually part of its solid crystal structure. This stuff is a real workhorse in industries that make glass, soap, and paper. And at home, it's a great cleaning agent, especially for softening hard water, which lets your soap and detergent work way more effectively.
And finally, plaster of Paris. Its full chemical name is calcium sulfate hemihydrate. Hemi just means half because it has half a water molecule in its chemical structure. The magic of this stuff is simple. You mix the white powder with water and it undergoes a chemical reaction, setting into a hard, solid mass we call gypsum. This unique property is why it's so perfect for setting broken bones in a cast, but also for making decorative moldings or creating smooth surfaces on walls.
And that's a wrap. We've journeyed from the simple definitions of acids and bases all the way to the major industrial chemicals they help create. It all comes back to this idea of balance, which leads me to one last question for you. We've seen how acids and bases neutralize each other in a beaker. Where else in your daily life do you see this fundamental